Chapter 6.2, Sum Difference Identities for Sine and Cosine. There are sum and difference identities for the sum and difference of any two angles, alpha and beta, or A and B. The sum identities, and these are all on your formula sheet. Sine of A plus B equals sine A times cos B plus cos A times sine B. Cos A plus B equals cos A times cos B minus sine A times sine B. And tan A plus B equals tan A plus tan B divided by 1 minus tan A times tan B. And the difference identities are sine A minus B equals sine A cos B minus cos A sine B, and cos A minus B equals cos A cos B plus sine A sine B, and then tan A minus B equals tan A minus tan B over 1 plus tan A tan B. We also have double angle identities. Sine 2A equals 2 sine A cos A. Cos 2A equals cos squared A minus sine squared A, or cos 2A equals 2 cos squared A minus 1, or cos 2A equals 1 minus 2 sine squared A, and tan 2A equals 2 tan A over 1 minus tan squared A. Again, all of these are on your formula sheet, so you're going to be referencing your formula sheet a lot while you're working on these problems. These identities can be used to determine the exact values of some sine and cosine ratios. Determining exact trig values for angles. Example, use a sum or difference identity to find the exact values of sine of 15 degrees. 15 degrees is not one of our special angles. What we want to do is write 15 degrees as the sum or difference of two of our special angles. Then sine of 15 degrees equals sine of 60 degrees minus 45 degrees, or 45 degrees minus 30 degrees. Either one of those would work. Then the difference identity for sine tells us sine A minus B equals sine A cos B minus cos A sine B. We have sine of 60 minus 45. That would equal sine of 60 degrees times cos of 45 degrees minus cos of 60 degrees times sine of 45 degrees. Now we need to determine the values of sine 60 and cos 45. You can draw either your special triangle or the first quadrant of the unit circle. Our 45-degree angle is between the two axes. One of our angles has a y value of 1/2. And the other one of our angles has an x value of 1/2. So the smallest angle is 30 degrees, which had a y value of 1/2, means the x value is root 3 over 2. Then the next angle is 45 degrees, and that has x and y values of root 2 over 2. And our next special angle is 60 degrees, which has an x value of 1/2, so then the y value is root 3 over 2. And the x value is cos, and the y value is sine, cos, sine. So then sine of 60 degrees, that's our biggest of the three angles, is the y value, which is root 3 over 2. So this becomes root 3 over 2 times cos of 45 degrees is root 2 over 2 minus cos of 60 degrees is 1/2 times sine of 45 degrees is root 2 over 2. And we simplify that. Root 3 times root 2 is root 6 over 2 times 2 is 4 minus 1 times root 2 is root 2 over 2 times 2 is 4. And we can put that into one fraction, which equals root 6 minus root 2 divided by 4. And that is sine of 15 degrees. Next, cos of 165 degrees. We want to split that up into angles that have reference angles that are the special angles. So I could write it as cos of 120 degrees plus 45 degrees. Then that equals the sum identity for cosine, cos A plus B equals cos A cos B minus sine A sine B. So cos of 120 degrees times cos of 45 degrees minus sine of 120 degrees times sine of 45 degrees. Then I need to know the values of sine and cosine for 45 degrees and 120 degrees. I already know sine and cos for 45 degrees because I have it over here. It's root 2 over 2 and root 2 over 2. Sine and cos are the same. And then for 120 degrees, is in quadrant 2, and it has a reference angle of 60 degrees. Reference angles of 60 degrees have x values of 1/2 and y values of root 3 over 2. And then because it's in quadrant 2, we have a negative x value. So negative 1/2 and positive root 3 over 2. This is our cos and this is our sine. Then we can substitute those values into our equation. Cos of 120 degrees is negative 1/2 times cos of 45 degrees, which is root 2 over 2, minus sine of 120 degrees is root 3 over 2, times sine of 45 degrees, which is root 2 over 2. Then we simplify. Negative 1 times root 2 is negative root 2 over 2 times 2 is 4, minus root 3 times root 2 is root 6 over 2 times 2 is 4. And then we get cos of 165 degrees equals negative root 2 minus root 6 over 4. Tan of 11 pi over 12. When using the sum difference identities, it's often easier to work in degrees, so we can convert 11 pi over 12 to degrees. 11 pi over 12 times 180 degrees over pi. Pi's divide out. we get 180 times 11 divided by 12. Bring up our calculator. 180 times 11 divided by 12 gives us 165 degrees. And that's the same as the last one, so we can write this as tan of 120 degrees plus 45 degrees. The sum identity for tan is tan A plus B equals tan A plus tan B over 1 minus tan A tan B. That gives us tan of 120 degrees plus tan of 45 degrees over 1 minus tan of 120 degrees times tan of 45 degrees. We need to determine the value of tan at 120 degrees and at 45 degrees. We should know that at 45 degrees, tan is equal to 1 because our x and y values are the same, both root 2 over 2. Then for tan of 120 degrees, 120 degrees has a reference angle of 60 and it's in quadrant 2. The point is then negative 1/2 and root 3 over 2. That's cos, that's sine. Then tan of 120 degrees equals our opposite, which is our sine, over cos, which equals root 3 over 2 divided by negative 1/2. Multiply by the reciprocal, we get root 3 over 2 times 2 over negative 1. 2's divide out. We get root 3 over negative 1, which is just negative root 3. So tan of 120 is negative root 3. Then we can sub these values into our equation. We have tan of 120 is negative root 3 plus tan of 45 is 1 divided by 1 minus tan of 120 is negative root 3 times tan of 45 is 1. Simplify and we get negative root 3 plus 1 over 1 plus root 3. Then we rationalize the denominator by multiplying by the conjugate, 1 minus root 3 on top and bottom. The top we get negative root 3. Negative root 3 times negative root 3 is plus the whole number 3. 1 times 1 plus 1. And then 1 times negative root 3 is negative root 3. On the bottom, we get 1 times 1 is 1. 1 times negative root 3 is negative root 3. Root 3 times 1 is positive root 3. And then root 3 times negative root 3 is negative whole number 3. The middle terms add to 0. Then we get 3 plus 1 is 4 minus root 3, so minus 2 root 3 over 1 minus 3 is negative 2. And then we can divide each of our coefficients, 4, 2, and 2. We can divide those all by 2. So we are left with 2 minus 1 root 3 over negative 1 And I don't need to write that as a fraction. I could write this as negative 2 minus root 3, and then I can multiply the negative into the brackets to get negative 2 plus root 3. So we have tan of 11 pi over 12 equals negative 2 plus root 3. Cos of negative pi over 12. Again, I think it's easier to work with degrees when we're using sum and difference identities. I'm going to change negative pi over 12 to degrees by multiplying by 180 over pi. The pi's divide out. I get negative 180 divided by 12. Negative 180 divided by 12 gives me negative 15. Then I can write this as cos of negative 15 degrees equals cos of, I could write 30 degrees minus 45 degrees, or I could write 45 degrees minus 60 degrees, either one of those. The difference identity for cos is cos A minus B equals cos A cos B plus sine A sine B. So this equals cos 30 degrees times cos 45 degrees plus sine 30 degrees times sine 45 degrees. We already know that sine and cos of 45 degrees are pi over 2, and we want to know sine and cos of 30 degrees. Can look back at the first one we did where we drew our quadrant 1. We have 30 degrees, x is root 3 over 2, and y is 1/2. So that's our cos and sine. Then we can sub in the values. Cos 30 is root 3 over 2. Cos of 45 is root 2 over 2. Plus sine 30 is 1/2. And sine 45 is root 2 over 2. Simplify, we get root 6 over 4 plus root 2 over 4, which gives us root 6 plus root 2 over 4, and that is cos of negative pi over 12. Simplifying expressions using sum difference identities. The sum and difference identities can be used to determine the exact values of some sine and cosine ratios. Example, simplify each expression as a single trigonometric function. We have cos 8x times cos 2x plus sine 8x times sine 2x. Notice that we have 8x, 8x, and then 2x, 2x. So we could call that A is 8x and B is 2x. Then if we look at the last page at our sum difference identities, where do we have cos A cos B plus sine A sine B? That would be here, cos A cos B plus sine A sine B, and that's equivalent to cos A minus B. So then we can write this as cos A minus B, which equals cos A is 8x minus angle B is 2x which gives us cos of, those are like terms, 8x minus 2x gives us 6x. And now we have a single trigonometric function, cos 6x. Sine of pi over 2 minus x, that is a difference, so we can use the difference identity. Sine A minus B is sine A cos B minus cos A sine B. Pi over 2 is A and x is B. Then we have sine A, which is pi over 2 times cos B, which is x, minus cos A, which is pi over 2 times sine B, which is x. What is the value of sine and cosine at pi over 2? This point is pi over 2. That's the positive y-intercept, which has an x value of 0 and a y value of 1. And that's our cos and then sine. So sine of pi over 2 equals 1. And then cos x minus cos pi over 2 is 0. And then sine x, but 0 times anything is 0. So we're just left with 1 cos x, which is just cos x. And now we have a single trigonometric function. Determine the exact value for the following expression. Sine 2 pi over 3 times sine pi over 12 minus cos 2 pi over 3 times cos pi over 12. So notice we have 2 pi over 3, 2 pi over 3, we'll call that angle A. And then we have pi over 12, we'll call that angle B. We have sine A times sine B minus cos A times cos B. Does this look like one of our sum difference identities? For the cos identity, we have cos A plus B equals cos A cos B minus sine A sine B. So notice the order here is opposite of our order. And then for cos A minus B, we have cos A cos B plus sine A sine B. So this is opposite order and it's a plus instead of a minus. We can change the order of our subtraction by factoring out a negative. So let's do that, and then it will match cos A plus cos B. If we factor out a negative, we get negative bracket. Now we'd have negative sine 2 pi over 3 times sine pi over 12, and then plus cos 2 pi over 3 cos pi over 12. Then we can switch the order of the binomial. We get negative bracket cos 2 pi over 3 cos pi over 12 minus sine 2 pi over 3 sine pi over 12. Now this cos A cos B minus sine A sine B now is the sum identity for cos. We have cos A cos B minus sine A sine B. So we can write this as negative cos angle A 2 pi over 3 plus pi over 12, which is negative cos 2 pi over 3, multiply top and bottom by 4 to get a denominator of 12. We get 8 pi over 12 plus pi over 12, which gives us negative cos 9 pi over 12. Simplify the fraction to get negative cos 3 pi over 4. Then we want to determine the value of cosine at 3 pi over 4. Three pi over 4 has a reference angle of pi over 4. We have 0, pi over 2 here, which equals 2 pi over 4. Pi is here, which equals 4 pi over 4. So 3 pi over 4 would be halfway in between in quadrant 2. Reference angle of pi over 4, we have root 2 over 2, root 2 over 2, but in quadrant 2 the x value is negative. So there's our point. This is our cos, is the x. So negative cos 3 pi over 4 equals negative root 2 over 2, which equals root 2 over 2. Simplifying expressions using double angle identities. Determine an identity for cos 2a that contains only the sine ratio. First of all, let's figure out what the identity for cos 2a is. We have three different ones. Cos 2a equals cos squared a minus sine squared a, or cos 2a equals 2 cos squared a minus 1, or cos 2a equals 1 minus 2 sine squared a. This is what the question is asking us to do. It's asking us to write it in terms of just sine a, so we're going to end up with this. But let's start here and see how we get to this. So cos 2a equals cos squared a minus sine squared a. So we want to rewrite this in terms of sine. We know that cos squared a plus sine squared a equals 1. That's our Pythagorean identity for trig. We can isolate cos squared a by subtracting sine squared a from both sides. Then we get cos squared a equals 1 minus sine squared a. Then we can replace the cos squared a here with 1 minus sine squared a. So we get cos 2a equals 1 minus sine squared a minus sine squared a. These are like terms. They're each negative 1, so we have cos 2a equals 1 minus 2 sine squared a. Write each expression as a single trigonometric function. 2 sine pi over 12 cos pi over 12. We have the same angle, so we could call that a. So we have 2 sine a cos a. If we go back to our identities and look for 2 sine a cos a, 2 sine a cos a is sine of 2a. Then we can write this as sine of 2a, which equals sine of 2 times pi over 12, which equals sine of pi over 6. One minus 2 sine squared 3a. Let's just call this angle B for now. So 1 minus 2 sine squared of an angle. Let's look for that in our identities. We have 1 minus 2 sine squared of an angle here, and that is equal to cos 2 of the angle. We called our angle B, so we can write equals cos 2b, cos 2 of angle B. Then we can sub in angle B. We get cos 2 times angle B is 3a, which gives us cos 6a. Simplify sine 2x over cos 2x plus 1 to one of the three primary trig identities and state the Npvs. So we want to get it down to either sine, cos, or tan x. I have sine 2x in here and also cos 2x in here. So let's go back to our identities and see what sine 2x is. Sine 2a is 2 sine a cos a. So sine 2x is 2 sine x cos x, and then we want to know what cos 2x is. So cos 2a, we can use cos squared a minus sine squared a, or 2 cos squared a minus a, or 1 minus 2 sine squared a. We can use any form of cos 2a, and we will get the same answer in the end. I'm going to choose 2 cos squared a minus 1. It's 2 cos squared x minus 1. Then I can write sine 2x over cos 2x plus 1 as sine 2x is 2 sine x cos x, and then cos 2x is 2 cos squared x minus 1, and then we also have plus 1. Then I can simplify minus 1 plus 1, those add to 0. I get 2 sine x cos x over 2 cos squared x. We can divide out the 2's. We get sine x cos x over cos squared x. Then we can divide out cos x from top and bottom. On the bottom, it would just get rid of the squared because that's cos x times cos x. So now I have sine x on the top and cos x on the bottom. And sine x over cos x is tan x. We also need to state the Npvs. So any denominator we have along the way cannot equal to 0. We have cos 2x plus 1. That cannot equal to 0. Cos 2x plus 1 cannot equal to 0, which means cos 2x cannot equal negative 1. And then we have cos x on the bottom. So cos x cannot equal 0. For cos x not equal to 0, when is x equal to 0? That is at pi over 2 or 90 degrees. It doesn't say what we're in here, so x cannot equal pi over 2 plus pi n, where n is an element of the integers, or x cannot equal 90 degrees plus 180 degrees n, where n is an element of the integers. And then for cos 2x cannot equal -1, when is cos equal to -1? Cos is the x value, which is -1 at pi or 180 degrees, and every 2 pi or 360 degrees after that. So we would say that 2x cannot equal pi plus 2 pi n, where n is an element of the integers. But then we divide everything by 2, 2, 2, and 2, and we get x cannot equal pi over 2 plus pi n, where n is an element of the integers. So that just gets us back to the same non-permissible value we had up here. And the same would happen for doing it in degrees as well. We would get back to the same place. So our Npvs, we've checked both denominators that we have, and the general statement for the Npvs for this question are these. That brings us to the end of Chapter 6, Lesson 2.